Students, today I'll explain to you how to find out minimum solvent flow rate in a single stage liquid-liquid extraction or solvent extraction process. Interestingly, it's quite different from finding out minimum solvent flow rate for a countercurrent multi-stage operation where Hunter-Nash graphical method is used. So the overall technique that I'm going to demonstrate is a graphical method, but since it is a single stage process, the steps are quite different. Now to explain that, first let me draw the schematic of a single stage mixer settler unit along with all the streams. So this is a typical single stage mixer settler unit and various associated streams. As you can see from the figure, the feed stream enters, the corresponding concentration of solute in the feed stream is XF. The solvent stream is shown. Accordingly, the solute concentration in the solvent stream is YS. If the solvent is a pure solvent, the value of YS is going to be equal to 0. So this is basically a mixture where the feed and the solvent streams are brought into intimate contact. After that, the mixed stream originates in the exit and the corresponding concentration of the solute in the mixed stream is Xm. And then the mixed stream goes into a settler unit where the extract and the raffinate phases settles down, and from the top we get the extract product. The symbol for extract stream is E, corresponding concentration of solute in the extract stream is Ye, and the raffinate stream is denoted by R and corresponding concentration is XR. Now here one should understand why determination of minimum solvent flow rate is important. Now for a designer, the feed condition should be well defined in the beginning. The feed flow rate, corresponding concentration of the solute in the feed must be known to a designer. Accordingly, the final raffinate composition and the raffinate flow rate should also be given or known to a designer, based on which the designer will design the process. The only thing which remains open to the choice of a designer remains the solvent stream. So one can select a suitable solvent, one can change or manipulate the solvent flow rate, and hence, and of course, the purity of the solvent stream. And for that reason, the minimum solvent flow rate should be known because the actual solvent flow rate should be above the minimum solvent flow rate. And the thumb rule suggests that the value of the operational solvent flow rate or optimum solvent flow rate is roughly 1.1 to 1.5 times the minimum. Okay, now first let us see how to find out the minimum solvent flow rate. Now according to the schematic, let us do an overall material balance and a component balance for two different scenarios. In the first scenario, suppose the overall solvent flow rate is given, so the material balance will be F plus S is equal to M is equal to E plus R. Now since we are largely focusing on finding out the solvent flow rate, we'll consider this part of the equation. Now if you do the component balance, the equation will look like this: Fxf plus Sys is equal to Mxm. From here you can easily get an expression for mixed stream, which is Xm equal to Fxf plus Sys divided by M, which can be written as Fxf plus Sys divided by M basically is equal to F plus S. Let it be equation 1. So finding out the mixed stream concentration and hence the location of mixed stream is important in the graphical method, and we'll see how later on. Okay. Now for a minimum condition, the equation will look like this: F plus S minimum is equal to M. We are focusing on the mixer part of the unit. Okay. If you do the component balance, it's going to be Fxf plus S minimum Ys is equal to M. Let it be Xm prime. Okay, under a different condition, let's say the corresponding concentration of the mixed stream be Xm prime. From here, we can easily find out an expression for S minimum, which is going to be equal to S minimum Ys is equal to M is nothing but F plus S minimum Xm prime minus Fxf is equal to S minimum Ys minus Xm prime is equal to F Xm prime minus Xf. Okay, and from here you get the final expression for minimum solvent flow rate. S minimum is equal to F multiplied by Xm prime minus Xf divided by Ys minus Xm prime. So let it be equation 2. So if you can locate Xm prime point in the graph and Xf values, Xf and Ys values are known, F, the value of feed flow rate, is already given, you can easily find out the value of S minimum. Okay. Now to do the graph, first of all we have to define the ternary system. Okay. So let us say it's a type 1 type ternary system. It's a type 1 type ternary system. Now if I say type 1 type ternary system, it basically means that there are three components. C stands for solute, A stands for carrier, and B stands for solvent. In a type 1 ternary system, the carrier and the solvent pair are partially miscible into each other. Okay, so this combination is partially miscible, whereas the other two pairs, the solute in carrier and the solute along with the solvent, are completely miscible into each other. So that's a typical type 1 ternary system condition. Now based on this condition, when you carry out the liquid-liquid equilibrium study, we come across a typical binodal type of liquid-liquid equilibrium plot. Now let us demonstrate such a plot within a right angle triangular diagram. So let me first draw a right angle triangle. Let us say the x-axis represents the solvent condition. It is the weight fraction of the solvent, 0 to 1, 0 to 1, and the y-axis is represented by this line, which is xcyc. So this represents the weight fraction of component C. Now a typical binodal type ternary plot will appear like this. Okay, so if suppose P is the plate point, the left of the plate point is the raffinate arm and the right of the plate point is the extract arm. Okay, so once you plot the LLE within the right angle triangular diagram, Then you locate first the feed point, so let it be the feed point. Okay, then you locate the solvent point, assuming the solvent is a pure solvent, it is the vertex of the triangle, so this is the solvent point. Now already I have shown you this equation, F plus S is equal to M earlier in the total mass balance. So the step involves joining Fs point and we get the Fs line. After that, as per the equation, location of M point will be on the Fs line. So if you know the xm value, you can easily locate the M point on the Fs line. Now comes the most interesting part, how to find out S minimum. Now you understand that in the mixer unit, both feed and the solvent goes, and the solvent flow rate is slowly and slowly decreased until it reaches a minimum value. If the value of S decreases, the locus of point M will slowly shift towards the feed point. You may also check it using this equation, xm is equal to fxf plus sys divided by f plus s. If the value of solvent is decreased slowly till it reaches S minimum, the corresponding value of xm increases and the point will gradually move towards the feed point. So as it moves towards the feed point, there will be a condition or there will be a situation when this M point will touch and exactly lie on the equilibrium line. So let it be the M prime point. Now if you want to decrease the solvent flow rate even further, the M point, which becomes M prime on the equilibrium line, will move into the single phase region, which is basically the homogeneous region, meaning the solvent and the feed becomes completely miscible into each other, and if that is so, separation by solvent extraction is not possible, because under the dome in the binaural plot, this is the two-phase region, heterogeneous area. Beyond this, it is the homogeneous area. So if you keep on decreasing the solvent flow rate, there will be a time when the mixed feed point will slowly and gradually move towards the feed point till it reaches the equilibrium line at it intersects or superimposes or coincides with the line, and that's the last point. It cannot be less than that, because if it is lesser than that, this point, M prime point, will shift into the or move into the homogeneous miscible region, and separation by solvent extraction is not possible. So M prime is the last point which basically coincides with the equilibrium line. Corresponding to the M prime point, you move towards the y-axis, find out the concentration xm prime. Once you find out the concentration xm prime, you use the equation as has been shown earlier. S minimum is equal to f of xm prime minus xf divided by ys minus xm prime. Okay, xm prime is known from the graph, f value is given, ys is known, xf is given, and we can easily find out the value of S minimum, and then you can find out S actual by multiplying with a suitable multiplying factor. So in a nutshell, to find out the value of minimum solvent flow rate, just you plot the LLE in a right angle triangular diagram. Okay, locate the feed point, locate the solvent point, join feed with the solvent point, okay, and just find out this point of intersection of Fs line with the equilibrium line, which will give you the M prime point, and the corresponding concentration is going to be xm prime, and you put the value of xm prime in the equation and find out the value of S minimum. Isn't it very interesting? Now, before I wind up, here is a question for you. The opposite of minimum solvent flow rate is the maximum solvent flow rate. Now, please try to find out the value of S maximum using the graph, and you can share your thought in a comment. Thank you very much.